On October 21st, 2025, an image appeared on the internet that should not exist. Not a comet, not an asteroid. Something else, entirely hanging in the blackness near our sun, wrapped in symmetrical light. Along its spine, bright nodes glowed with deliberate spacing. No fuzzy halo surrounded it. No tail of dust stretched behind. Just this sleek form suspended in space like it was parked there. Watching. The object is called 3I Atlas, discovered on July 1st, 2025 by the Atlas Survey Network. It's the third confirmed interstellar visitor to breach our solar system. For 3 months, astronomers tracked it as it fell sunward, cataloging its chemistry, measuring its trajectory. Everything pointed to comet. Unusual chemistry, certainly, but still a comet. Then this image leaked. And here's what makes the timing so suspicious. 3I Atlas is approaching perihelion, its closest pass by the sun, during a week-long window when Earth-based telescopes will be essentially blind. Solar conjunction. The sun sits directly between us and the object, flooding our instruments with blinding light. It's the perfect blackout. The perfect moment to hide something, or to do something. If you wanted to execute a maneuver near the sun without Earth watching, this is precisely when you do it. Tonight, we're going to examine everything we know about 3I Atlas, the verified science, the leaked imagery, the independent amateur observations, the chemistry that doesn't quite fit, the trajectory that seems too convenient, and the maneuver, the orbital trick called the Oberth effect, that could explain why any intelligence would send a probe skimming past our star at this exact moment. The stakes are simple. If this object is natural, it's a fascinating anomaly that will teach us about the diversity of interstellar space. But if it's artificial, if what we're observing is technology from beyond our solar system, then the next few weeks might answer the oldest question humanity has ever asked. Are we alone, or has someone been watching us all along? Stay with me, we have a long night ahead. And by dawn, you'll understand why some astronomers can't sleep. Let's begin with what we know for certain. There are 3 things in the known universe that travel between stars. Radiation photons crossing the void at light speed, cosmic dust, microscopic grains drifting through the galaxy over millions of years. And apparently, something else. Something larger. Something that arrives from the darkness beyond our solar system and passes through our neighborhood like a messenger we never expected. We call them interstellar objects. And until very recently, they were purely theoretical. Think about the scale here. The nearest star system to our sun, Alpha Centauri, is 4.3 light-years away. That's 25 trillion miles of empty space. The galaxy contains hundreds of billions of stars, each separated by distances so vast that if you picked a random direction and threw something, the odds of it hitting our solar system would be effectively 0. Space is not just empty, it's profoundly empty, and yet they come. The first confirmed interstellar visitor arrived in October 2017. Astronomers at the University of Hawaii spotted it streaking through the inner solar system, moving far too fast to be bound by the sun's gravity. They named it Wani Umuamua Hawaiian for scout, or messenger from afar arriving first. Its trajectory was hyperbolic. It came from the direction of the constellation Lyra, passed within 15 million miles of Earth, swung around the sun, and departed. We'll never see it again. But here's what made Oumuamua strange: its shape and its motion. Observations suggested an extreme elongation, perhaps 10-to-1 length-to-width ratio, a cosmic cigar tumbling through space. And as it moved away from the sun, it accelerated slightly more than gravity alone could explain. Comets do this. Sublimating ice creates jets that nudge their orbits. But Oumuamua showed no coma, no tail, no evidence of outgassing. So, what was it? A comet with unusual composition? An interstellar asteroid? Or something else? The debate raged for years. Dr. Avi Loeb, chair of Harvard's astronomy department, published a paper suggesting it could be a light sail, a thin reflective membrane pushed by starlight, artificial, deliberate. The scientific community pushed back hard. Extraordinary claims require extraordinary evidence, and the data was ambiguous. But the questions lingered. Then, in August 2019, the second visitor arrived. 2I Borisov was different. It looked like a comet. It behaved like a comet. It had a coma. A tail's spectroscopic signatures matching known cometary chemistry. This one made sense. An icy wanderer from another star system doing exactly what comets do. It reassured us. The universe was strange, yes, but still comprehensible. And now, 3I Atlas, discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short. This is a network of telescopes in Hawaii and South Africa designed to scan the sky for asteroids that might threaten Earth. They survey thousands of square degrees each night, hunting for anything that moves. When they found 3I Atlas, it was still far from the Sun, approaching from interstellar space at 39 kilometers per second. That velocity told the story immediately. Objects gravitationally bound to our Sun comets from the Oort cloud asteroids from the main belt move at predictable speeds, but 39 kilometers per second is too fast. The orbit is hyperbolic, not elliptical. This object came from outside. It will pass through and leave, never to return. For 3 months, astronomers tracked it. The James Webb Space Telescope pointed its infrared eyes at the object. Hubble captured optical and ultraviolet spectra. The Very Large Telescope in Chile and the Keck Observatory in Hawaii obtained high-resolution spectroscopy. Every major observatory with access to the southern sky dedicated time to observing this visitor. And what did they see? A comet. A fuzzy, diffuse object surrounded by a cloud of gas and dust. Evidence of outgassing driven by solar heating. Spectroscopic signatures of cyanide and strangely atomic nickel. The chemistry was unusual. We'll explore why in detail later, but the morphology was standard. Coma, faint tail evidence of sublimating ice. Nothing metallic, nothing structured, just a comet. That was the consensus. The official scientific understanding. 3I Atlas, an interstellar comet with interesting chemistry. Worth studying, certainly, but fundamentally natural. Then, October 21st happened. An image surfaced online, grainy, compressed, watermarked with a cryptic code UFO 5537, allegedly leaked from a Japanese observatory or space agency. And what it showed was nothing like what professional telescopes had been reporting. It showed something that looked engineered. The image depicted an elongated, spindle-shaped object near the Sun. No coma, no diffuse cloud of gas, no tail. Instead, a rigid form with bright nodes running along its central axis, evenly spaced, glowing with blue-white intensity. The entire structure was wrapped in a luminous sheath that looked less like reflected sunlight and more like powered emission. It looked like a spacecraft, and the timing. Here's what makes this moment so extraordinary. The timing coincided with 3I Atlas approaching the one place in the solar system where an advanced probe would want to be if it were performing a high-energy maneuver, perihelion, the closest approach to the Sun, the optimal location for what orbital mechanics calls the Oberth effect, the most efficient way to change your velocity using a gravity well. But we're getting ahead of ourselves. First, we need to understand what happened on October 21st. We need to examine that image in detail. We need to trace its provenance, evaluate its credibility, and compare it to everything else we know about 3I Atlas. Because if that image is real, if it accurately depicts what's approaching our Sun right now, then everything changes. The universe becomes stranger. Lonelier, perhaps. Or suddenly very crowded. Let's examine the leak. The clip started appearing on social media around mid-morning Eastern Time on October 21, 2025. Users with varying degrees of credibility began sharing it, some breathless with excitement, others cautiously skeptical. The footage was brief, grainy, compressed through multiple rounds of encoding. But what it showed was unmistakable enough to ignite a firestorm. You're looking at an object near the Sun, The field of view suggests solar-adjacent observation, the kind of imaging you'd get from a coronagraph or heavily filtered solar telescope. The background is deep black. Stars are absent, washed out by processing or by the overwhelming light of our star just off frame. And there, hanging in that darkness, is it? An elongated form. The aspect ratio is high length significantly exceeds width. Not a sphere, not an irregular tumbling rock. A spindle, a rod, something with deliberate geometry. Along the central axis you see them, bright points.
Not a continuous glow, not random scattering of light, discrete nodes, 6, maybe 7 of them, depending on how you count. They're evenly spaced. The intervals look regular, geometric. Each node glows with similar intensity and color. A white blue that suggests either reflected sunlight at a very specific angle or something else. Emission, power. The spacing is what catches your eye. Your pattern recognition circuits those ancient neural pathways that evolved to spot predators in tall grass and faces in shadows. They scream deliberate. Nature rarely does this. Crystals exhibit regular spacing at microscopic scales. Molecular structures show periodicity, but macroscopic objects made of ice and rock, they don't self-organize into evenly spaced glowing points. Then there's the sheath. A blue-white luminosity wraps the entire structure, creating a halo effect. It's uniform. The brightness doesn't vary dramatically from one end to the other.
There's no obvious bright nucleus that you'd expect from a solid reflective core surrounded by diffuse gas. Just this smooth, distributed glow that makes the whole thing look illuminated. From within, from surface features, from some kind of powered system managing heat or propulsion. You try to see a comet in this image, you really do. You look for the fuzzy coma, the extended tail, the asymmetric jets that every comet you've ever studied exhibits. They're not there. What you see instead is coherence, structure, a form that reads as designed rather than accumulated. In the lower corner, the watermark. UFO 5537, it sits there like a digital signature, telling you nothing about origin, but everything about intent. Watermarks can be added by anyone to anything. They don't authenticate content, they just mark it. And this marking feels performative, as if someone wanted you to know this was labeled unidentified. If you were leaking classified data, would you stamp it with a code that screams conspiracy, or would you strip metadata? Anonymize the source, distribute through secure channels, and let the content speak for itself. The watermark raises questions, but it doesn't answer them. Anonymous posts claim the footage originated from Japan. Some say JAXA, the Japan Aerospace Exploration Agency. Others mention university observatories, solar monitoring networks, private research facilities. The stories vary, the details shift, but the thread remains consistent. This allegedly came from Japanese instruments observing the sun on or around October 20th, 21st. So you go looking for official confirmation, press releases from JAXA, data embargo announcements from Japanese observatories, instrument logs matching the timestamp or field of view, weather reports from that night confirming clear skies at potential observation sites. You find nothing. No official statement, no acknowledgement.
No denial, just silence. This is where provenance becomes critical. Real astronomical data doesn't look like this clip. Professional observations come packaged with context. They arrive in FITS format, flexible image transport system, a standardized file structure that includes not just the image but extensive metadata. Every FITS file has a header listing the telescope, the instrument, the filter used, the exposure time, the observation date, and time stamped to the second. It includes the right ascension and declination of the pointing center detector temperature gain settings, observer's name, program identification number. It's a forensic gold mine. If someone leaked a genuine FITS file from a professional observatory, astronomers could verify its authenticity within hours. They'd check whether the star field matched the claimed coordinates.
They'd verify the point spread function, the characteristic way that telescopes' optics blur point sources against known profiles. They'd cross-reference weather records from that night to confirm seeing conditions matched the image quality. A real leak would be verifiable. What we have instead is a processed video clip, compressed, filtered, stripped of all the forensic details that would anchor it in reality. No FITS header, no metadata, no way to trace it back to a specific instrument or observation sequence. That's suspicious. It's consistent with either a hoax, someone created the clip digitally and added a fake watermark for credibility, or a deliberately sanitized leak where someone stripped identifying information to protect the source. Both scenarios are possible. Neither can be ruled out, but here's what makes this leak impossible to dismiss. Outright, it wasn't alone. On October 20th, one day, before the viral clip surfaced, an amateur astronomer named Tiago posted a raw frame from his solar telescope.
He goes by Dobsonian Power online, a handle that reflects his passion for large aperture manual telescopes, typically used for deep sky observation. But Tiago also maintains solar imaging equipment. And on that October morning, he pointed his scope at a specific set of coordinates, the coordinates for 3I Atlas. What he captured was unexpected. We'll examine his image in detail shortly, but for now, understand this. Tiago's observation showed anomalous morphology, a compact, bright region, a pronounced forward-facing structure, features that didn't match typical cometary appearance. And critically, Tiago is a known observer with a public track record. His post included timestamp coordinates equipment details. Other amateur astronomers cross-referenced his pointing solution with JPL's ephemeris and confirmed he was looking at the right location at the right time. This isn't an anonymous leak. This is traceable community-level verification. It's not agency-certified, peer-reviewed science data. But it's not nothing either. It's a data point. Two independent sources, one anonymous and controversial, one public and traceable, reporting similar morphological strangeness at the same celestial coordinates at nearly the same time. That's what gives the leaked image oxygen. That's what keeps it alive in the conversation, despite the lack of official confirmation. Because if only one person reported this, you could dismiss it as artifact, as processing error, as wishful thinking. But when multiple independent observers describe consistent features, the possibility space narrows. Either there's really something anomalous at those coordinates, or we're witnessing a coordinated hoax of unusual sophistication. So let's compare what the leaked image shows with what comets actually look like when serious telescopes observe them. Let's establish the baseline of natural behavior. And then we'll understand just how far outside that baseline this alleged footage sits, because the gulf between what professional observatories have been reporting and what that October 21st image shows, that gulf is where the mystery lives. Before we can evaluate the strange, we must understand the normal. Comets are fundamentally dirty snowballs. That's the colloquial description, and it's not far from the truth. They're small, typically a few miles across, at most composed, primarily of water ice, mixed with dust rock and frozen gases like carbon dioxide, methane, and ammonia. They form in the cold outer reaches of planetary systems where temperatures are low enough for these volatile compounds to remain solid. When a comet approaches the sun, solar radiation heats its surface. The ice doesn't melt. Space is a vacuum, so there's no liquid phase. Instead, it sublimates, transitioning directly from solid to gas. This process is vigorous. Gas escapes from the comet's surface, dragging dust particles along with it. The result is a cloud, the coma that can stretch tens of thousands of miles in every direction. Behind the nucleus, solar radiation pressure acts on the dust and gas. Light has momentum. When billions of photons strike dust particles, they push them away from the sun. This creates the tail, that iconic streamer that can extend for millions of miles across space. Some comets develop two tails,
a dust tail yellowish and curved following the comet's orbital path, and a plasma tail bluish and straight, pointing directly away from the sun as ionized gas follows magnetic field lines. These structures are dynamic, asymmetric, constantly evolving. Rotation causes different regions of the nucleus to face the sun, creating jets of gas that erupt irregularly. Sublimation isn't uniform. Some areas are more active than others. The result is a messy, chaotic appearance. Nature loves chaos. Nature makes lumpy, potato-shaped objects with random jets spraying in multiple directions. This is what professional telescopes see when they observe 3I Atlas. The James Webb Space Telescope observed the object in August 2025, while it was still more than 2 astronomical units from the Sun. JWST operates in infrared wavelengths sensitive to the heat signature of dust and the absorption lines of molecules. What did it detect? A coma, gas and dust surrounding a small central nucleus. Spectroscopic signatures consistent with carbon dioxide and carbon monoxide volatiles sublimating as the comet warmed. Crucially, JWST found that 3I Atlas is carbon-rich and water-poor at large heliocentric distances. Most solar system comets are water-rich. This difference suggests the object formed in a different stellar environment where the temperature profile favored CO2 ice over H2O ice. It's unusual, but it's within the range of astrophysical possibilities. Hubble Space Telescope captured optical and ultraviolet observations in September 2025. Hubble's high resolution allowed detailed imaging of the coma structure. What did it show? Fuzzy, diffuse. A bright central condensation surrounded by a less luminous envelope. Evidence of jets' narrow features extending from the nucleus, probably from active regions on the surface. Nothing that looked structured, nothing metallic. The Very Large Telescope in Chile used its Muse spectrograph to obtain spatially resolved spectroscopy, meaning they measured the chemical composition at different locations within the coma. They detected cyanide CN concentrated near the nucleus and extending outward in patterns consistent with sublimation-driven jets. They also detected atomic nickel, which we'll discuss in depth later, but the morphology, comet standard. Keck Observatory in Hawaii obtained high-resolution imaging through multiple filters. When you observe a comet in different wavelengths, blue light, green light, red light, infrared, you see different components. Green light isolates CN emission. Red light emphasizes dust continuum. By comparing these images, you can map the distribution of gas versus dust. For 3I Atlas, the results showed exactly what you'd expect from a comet gas close to the nucleus dust, more widely distributed, everything following the physics of sublimation and radiation pressure. Every major observatory that pointed at 3I Atlas saw the same basic picture. A comet, unusual chemistry certainly, but morphologically typical. So what does this mean for the leaked image? The leaked clip shows none of this. No fuzzy coma, no diffuse envelope, no tail extending away from the sun. Instead, a coherent, elongated object with discrete, bright points. Structure, symmetry. Features that suggest boundaries rather than gradients. The visual language is completely different. Now you might argue that filter choice and processing can dramatically change appearance. And you'd be right. If you observe a comet through a narrow band filter that isolates one specific emission line, say, the green light from CN, you suppress the dust continuum and emphasize the gas. The object looks smaller, brighter, more concentrated. You're seeing only part of the picture. If you apply aggressive image processing deconvolution algorithms designed to sharpen detail by mathematically inverting the telescope's point spread function, you can introduce artifacts, ringing around bright sources, phantom edges, patterns that aren't real but are artifacts of the algorithm trying too hard to extract signal from noise. Professional astronomers know this. They're cautious about over-processing. They validate results against raw data. They cross-check with multiple instruments. But even accounting for all these effects, even if you imagine the most favorable combination of filter selection, viewing geometry, and processing techniques, the leaked image is hard to reconcile with the established morphology of 3I Atlas. The professional observations show a fuzzy cloud with a central nucleus. The leaked image shows a rigid spindle with evenly spaced nodes. These aren't different views of the same thing. They're fundamentally different morphologies. So either the leaked image is fake, created by someone with enough skill to make it plausible, but ultimately artificial, or the leaked image captured 3I Atlas under conditions timing geometry instrumental configuration that revealed something the professional observations missed. Or, and this is where the speculation begins, there are two components to 3I Atlas. A natural cometry component producing the coma and outgassing. And something else, something inside the coma hidden by the gas and dust with a geometry that only becomes visible under specific observing conditions. We're not claiming any of these explanations as truth. We're mapping the possibility space. We're showing you where the data ends and the speculation begins. But before we dive deeper into morphology and speculation, we need to understand the blackout window. Because what happens next, what's happening right now as this documentary unfolds, is that 3I Atlas is approaching perihelion during the 1 week when Earth's telescopes cannot observe it clearly. The geometry is about to make observation nearly impossible, and that timing is either the most extraordinary coincidence or something else entirely. Imagine trying to photograph a candle flame while staring directly at a searchlight. That's solar conjunction. Perihelion closest approach to the Sun occurs around October 29th or 30th, 2025 for 3I Atlas. The object will pass within approximately 1.36 to 1.4 astronomical units of our star. That's about 130 million miles. Inside Earth's orbit, but outside Venus's. No collision course, no danger. Just a close pass through the inner solar system. But here's the problem from Earth's perspective during this time. 3I Atlas and the Sun occupy nearly the same position in the sky. When we say an object is in conjunction with the Sun, we mean the Sun sits between us and that object, or nearly so. The apparent angular separation becomes very small. And when you try to observe something that close to the Sun, you're fighting a losing battle against glare. The Sun is bright, unimaginably bright. Its surface radiates with the intensity of thousands of billion-watt power plants squeezed into an area smaller than a postage stamp at arm's length. When you point a telescope toward the Sun, photons flood, your optics saturating detectors creating internal reflections scattering through the optical path, overwhelming any faint object nearby. Astronomers deal with this regularly when observing Mercury and Venus. These planets orbit closer to the Sun than Earth does, so they're often lost in solar glare. When they pass behind the Sun, from our perspective, superior conjunction, we lose them completely for days or weeks. The light is simply too overwhelming. Specialized instruments can help. Coronagraphs use occulting disks to block the Sun's direct light, allowing observation of the corona and objects in the surrounding space. The Solar and Heliospheric Observatory, SOHO, orbiting the Sun-Earth L1 point, employs coronagraphs to monitor the solar environment continuously. These instruments can sometimes catch comets that pass very close to the Sun, the sun-grazer comets that dive within a few solar radii. But 3I Atlas isn't that close. At 1.4 AU, it's far outside the coronagraph's typical field of view. It's in the worst possible position, too far from the Sun to be captured by coronagraph imaging, but too close in apparent angle to be observed easily by conventional telescopes without contamination from solar glare. Add to this the observational challenges of low apparent elongation. When an object sits near the Sun in the sky, you can only observe it near sunrise or sunset when the Sun is close to the horizon. But observing near the horizon means looking through maximum atmospheric thickness. The air is turbulent. Heat rising from the ground creates shimmer. what astronomers call bad seeing that blurs images and ruins fine detail. Professional observatories on mountaintops choose their locations specifically to minimize these effects. Mauna Kea in Hawaii, the Atacama Desert in Chile, these sites are selected for stable, clear air. But even the best sites suffer degraded performance when observing objects at low elevation angles. So for approximately 1 week, surrounding perihelion from roughly October 25th through November 2nd, Earth-based telescopes are effectively blind to 3I Atlas. Not completely blind, determined observers with the right equipment and excellent timing might catch glimpses during brief windows at twilight, but sustained high-quality observation impossible. This is the blackout window, and this is where the conspiracy theories bloom, because the timing is convenient. If you were an advanced intelligence operating a probe through our solar system and you wanted to perform a maneuver without Earth watching, this is when you do it. The geometry hands you a natural curtain. The glare protects you. No human telescope can track your position with precision. No spectrograph can monitor your emissions for anomalies. For 1 week, you have operational security provided by the universe itself. Now we must be clear about something. This kind of reasoning, the timing is too convenient to be coincidence, is seductive but not scientific. Coincidences happen. The universe has no obligation to avoid situations that look suspicious to humans. Selection bias plays a role here. We're paying attention to 3I Atlas because it's interesting, so any unusual circumstance surrounding it feels meaningful. If 3I Atlas approached perihelion at a time of maximum observational visibility, say in the nighttime sky opposite the sun, would we notice? Would we be making a documentary about it? Probably not, unless the morphology were absolutely undeniable. The blackout makes the mystery more mysterious, but that doesn't mean the mystery is artificial. Still, the timing nags at you. And it's not just amateur speculation. Professional scientists have noted the coincidence. Dr. Avi Loeb, whose name you'll hear repeatedly in this story, has pointed out that 3I Atlas's trajectory brings it to perihelion at the optimal location for what's called an Oberth maneuver, the most efficient way to change velocity using a gravity well, and that maneuver happens during conjunction. We'll explore the Oberth effect in depth later. For now, understand this: if you're piloting a spacecraft through the solar system and you want to either accelerate to maximum escape velocity or decelerate to capture into orbit, you do it at perihelion. You fire your engines when you're moving fastest, when you're deepest in the sun's gravity well. That's where every joule of propellant energy gives you the maximum change in total orbital energy. And if you do it during conjunction, Earth can't watch. Space-based assets might catch something. SOHO's coronagraphs, designed to image the sun's corona, operate continuously and might capture 3I Atlas if it passes through their field of view. The STEREO mission, Solar Terrestrial Relations Observatory, consists of 2 spacecraft orbiting the sun at different positions, providing perspectives Earth doesn't have. If 3I Atlas appears in their wide-field imagers during conjunction, that data could reveal what happened. But these instruments aren't optimized for detailed imaging of faint, fast-moving objects. They're designed for solar physics monitoring, coronal mass ejections, studying solar wind, tracking large, bright comets. A small, potentially dim object at 1.4 AU might be at the edge of their detection threshold, and even if they capture something, processing and releasing that data takes time, weeks potentially. So we wait, we sit here on Earth blind behind our star, knowing that something is happening 130 million miles away, and we can't see it. The blackout window is open now, or will be depending on when you're listening to this. The object is approaching perihelion. The sun is sliding between us and it. The curtain is closing. And when it opens again, when 3I Atlas emerges on the other side in early November, we'll measure where it actually is. We'll compare that position to where Newtonian gravity says it should be. And we'll know if something burned, if velocity changed, if the trajectory deviated from predictions in a way that outgassing alone cannot explain. The test is coming. The data will tell us the truth. But for now, in this moment, we're in the dark. Literally, astronomically. The universe is hiding its cards. And into this blackout one day before conjunction began, an amateur astronomer in Brazil pointed his solar telescope at the predicted coordinates and captured something unexpected.
His name is Tiago. Online, he goes by Dobsonian Power, a username celebrating his preferred instrument, the Dobsonian telescope. These are large aperture, manually operated reflectors, beloved by amateur astronomers for their simplicity and light-gathering power. Perfect for observing faint galaxies, nebulae, and star clusters on dark nights far from city lights. But Tiago also maintains equipment for solar observation. And on the morning of October 20th, 2025, he did something unusual. He pointed his solar telescope at coordinates provided by NASA's Ephemeris system, the database that predicts the positions of solar system objects. The coordinates for 3I Atlas. What he captured was posted to his public astronomy forum later that day. The image is raw, unprocessed in the sense that he didn't apply aggressive enhancement algorithms.
What you see is what his detector recorded: a frame speckled with noise, hot pixels scattered across the field of view, the characteristic graininess of pushing a sensor to its limits, trying to extract faint signal from overwhelming background. This is normal for solar-adjacent imaging. When you're trying to capture a dim object near the sun, you're operating at the edge of your equipment's capability. You crank exposure time as long as possible without saturating on the solar disk itself. You increase gain to amplify weak signal. And when you do that, every imperfection in your detector lights up. Hot pixels, cold pixels, readout noise. It all becomes visible. But through that noise, there's structure, a compact, bright region, not diffuse, not fuzzy like a typical coma, concentrated, intense. And here's what caught attention: a pronounced forward-facing structure. Tiago described it as shield-like, a bright leading edge angled toward the sun. Behind this front section, you see a faint, conical puff of material, asymmetric, less luminous than the leading edge. It creates the impression of something moving through space, nose first, with a wake or exhaust trailing behind. Critically, there's no extended tail. At the distance 3I Atlas sits from the sun, solar radiation pressure should have pushed dust particles into a noticeable tail by now. Every comet at this distance shows some tail structure, but Tiago's image doesn't capture that. Just this concentrated front-heavy form with a short, diffuse wake. Now Tiago is not an unknown quantity. He's been posting observations to astronomy forums for years. His equipment specifications are listed. His location somewhere in Brazil is known. He provides timestamps with his images. Other amateur astronomers can and did verify his work by cross-referencing his pointing coordinates with JPL's Ephemeris data for 3I Atlas. The numbers match. He was looking at the right place at the right time. This is what citizen science looks like. Not agency-certified data with rigorous peer review, but not random internet noise either. It's traceable, verifiable within the amateur community, a data point that exists in the space between official science and pure speculation. Multiple observers in the amateur astronomy community examined Tiago's raw frame and noted the same features he did: front-brightening, compact morphology, no extended tail. Some suggested explanations: forward-scattering, viewing geometry effects, phase angle coincidence. Others remained puzzled. But here's what makes Tiago's observation important for our story. It appeared one day before the viral leaked clip. Independent observation, different equipment, publicly documented, and showing similar morphological strangeness, a bright, compact, forward-facing structure that doesn't look like typical cometary diffusion. Two data points don't make a proof, but they make a pattern worth examining. So what could explain Tiago's image naturally? First possibility: sunward jet. The hemisphere of 3I Atlas facing the sun is receiving maximum solar heating. Volatiles on that side sublimate, vigorously creating jets of gas and dust that erupt directly from the surface. If one of these jets points nearly along our line of sight, erupting toward us as we look past it toward the sun, it would appear as a bright, concentrated feature. The material flowing away from the nucleus hasn't had time to disperse widely, so it remains compact and intense. This would explain the front brightening. It's not artificial structure. It's active outgassing from the sun-facing side seen nearly head-on. Second possibility, forward scattering. Light scattering off small particles has directional preferences. Forward scattering, when you're looking in approximately the same direction that sunlight is traveling, enhances brightness dramatically. If 3I Atlas has a dust cloud concentrated on its sunward side, and if Tiago's viewing geometry happened to align with a forward scattering angle, the entire dust cloud would light up brilliantly. The effect is optical, not structural. The brightness isn't intrinsic. It's a consequence of geometry. Planetary scientists know this effect well. Saturn's rings brighten dramatically when Earth crosses the ring plane and sunlight backscatters toward us. The moon looks brightest at full phase when sunlight directly backscatters. Same principle. Third possibility phase, angle sweet spot. The angle between the Sun, 3I Atlas, and Earth affects how much light we see. At certain phase angles, small particles exhibit what's called opposition surge, a sudden increase in brightness when viewing conditions approach perfect backscattering geometry. If Tiago's observation happened at just the right phase angle, natural dust could appear artificially bright and concentrated. All three mechanisms are plausible. All involve known physics. None require invoking artificial structures. But, and here's where careful analysis matters, all three mechanisms predict certain things we could test. Forward scattering and phase angle effects change as geometry changes. If you observe the object from different angles at different times, the brightness distribution should shift predictably. Sunward jets should evolve as the nucleus rotates, bringing different active regions into and out of solar illumination. If subsequent observations show these predicted changes, the natural explanation holds. If the features remain static, if the bright shield persists, unchanged despite changing geometry and phase angle, then the natural explanations become strained. We don't have those follow-up observations yet. Not publicly anyway. The object is entering solar conjunction. The test observations that would resolve this question can't happen until November, when 3I Atlas emerges and becomes observable again. So we wait, again, always waiting. But Tiago's image did something important. It validated that something unusual is visible at the predicted coordinates. It confirmed that the leaked Japanese footage, whatever its provenance, is at least describing an object that exists in that location. It doesn't tell us what that object is, it just tells us it's there. And it looks strange. Now we need to understand the chemistry, because beyond morphology, beyond visual appearance, there's a spectroscopic puzzle that makes 3I Atlas genuinely anomalous, even in the natural interpretation. Professional observations detected something in the coma that shouldn't be there, or at least shouldn't be there in the ratios observed. Atomic nickel. Glowing in the coma without the iron that usually accompanies it. And that chemistry, that specific combination of elements and their relative abundances, is what keeps scientists puzzled even as they propose natural explanations. Let's talk about metals in space, and why nickel without iron is so very strange. Chemistry is storytelling written in atoms. Every spectrum tells you what's present, how much, how hot, how fast it's moving. When you point a spectrograph at a comet, you're reading its biography, where it formed, what conditions shaped it. What's happening to it now? The spectroscopy of 3I Atlas tells a strange story. Let's start with the normal part. Multiple observations detected cyanide, specifically the CN molecule, one carbon atom bound to one nitrogen atom in the coma. This is standard. CN is one of the most common molecules in comets. It forms naturally in the cold, radiation-soaked environment of interstellar space and molecular clouds. Carbon and nitrogen are abundant throughout the universe. When comets approach the sun, solar ultraviolet light breaks apart larger molecules containing carbon and nitrogen, liberating CN into the coma, where it fluoresces, absorbs sunlight, and re-emits it at characteristic wavelengths that spectrographs detect easily. You see CN in comets all the time. It's so common that astronomers use it as a diagnostic. The strength of CN emission tells you about the comet's activity level, how much gas it's producing. Nothing strange here. But then there's the nickel. Observations from both the Keck Observatory in Hawaii and the Very Large Telescope in Chile detected atomic nickel in the coma of 3I Atlas. Not nickel bound in molecules, not nickel locked in dust grains. Free nickel atoms hot enough to fluoresce, producing emission lines in the visible spectrum. Now, metals in comet comae aren't unprecedented. Several comets have shown emission lines from calcium, sodium, iron, and yes, nickel. These metals exist in the rocky and metallic grains embedded in cometary ice. When ice sublimates, it exposes these grains to direct sunlight. The grains heat up. At sufficiently high temperatures above about 1000 degrees Celsius, the metals vaporize, releasing atoms into the coma. So seeing nickel isn't the puzzle. The puzzle is seeing nickel without corresponding iron. In typical cosmic material, the stuff that makes up rocky planets, asteroids, meteorites, iron outnumbers nickel by roughly 20 to 1. The sun's composition reflects this ratio. The solar nebula from which our solar system formed had lots of iron, less nickel. They go together. They're chemically similar form, similar minerals, vaporize at similar temperatures. If you're heating up generic rocky grains, you should see both metals in your spectrum. Strong iron lines, weaker nickel lines ratio reflecting their natural abundance. But that's not what 3I Atlas shows. The nickel emission is prominent. The iron lines are weak or entirely absent depending on which observation you examine. It's backwards, inverted, as if something is preferentially releasing nickel without iron. And that's weird. So what's happening? Let's explore the hypotheses, starting with the natural explanation that has the most scientific support. Hypothesis 1. Carbonyl chemistry. The natural pathway. 60% weight. There exists a chemical process that can explain selective nickel emission. It involves a compound called nickel tetracarbonyl. The formula is NiCO4, one nickel atom bonded to 4 carbon monoxide molecules. This compound is well known in industrial chemistry. It's used in nickel refining through a process called the Mond process. The remarkable property of nickel tetracarbonyl is that it's a gas at relatively low temperatures. It forms when nickel-bearing minerals react with carbon monoxide under specific conditions, and it's thermally unstable, heating it or exposing it to ultraviolet light. Breaks it apart, releasing nickel atoms and carbon monoxide. Here's the key: iron doesn't form a similar stable carbonyl compound under the conditions present in cometary environments. The chemistry is different. Nickel makes NiCO4 easily. Iron doesn't.
So if you have an environment rich in carbon monoxide with temperatures and pressures in the right range, you can preferentially vaporize nickel without significantly affecting iron. And guess what? The James Webb Space Telescope found that is carbon monoxide rich at large heliocentric distances. It's also carbon dioxide rich and water poor compared to typical solar system comets. This is consistent with formation in an interstellar environment where CO and CO2 dominated over H2O ice. So here's the scenario. As 3I Atlas approaches the sun and heats up carbon monoxide sublimates, this CO comes into contact with nickel-bearing grains embedded in the ice. Under the right temperature and pressure conditions, likely in the near surface layers of the nucleus, nickel reacts with CO to form NiCO4. This gaseous compound escapes into the coma. Sunlight then photodissociates it, breaking the molecule apart and releasing free nickel atoms.
Those atoms fluoresce, producing the emission lines telescopes detect. Meanwhile, iron grains remain solid.
They haven't reached the higher temperatures needed to vaporize pure iron metal, and they don't participate in carbonyl chemistry the way nickel does. So you get lots of nickel emission, little iron emission. Mystery solved. This explanation is elegant. It invokes only known chemistry and physics. It requires conditions, CO-rich environment-specific temperature range that observations confirm exist for 3I Atlas. Several peer-reviewed papers discussing the object's spectroscopy mention carbonyl chemistry as the likely explanation. It's the hypothesis with the most scientific backing. If you're betting on what's true, you bet on this. Hypothesis 2. Unusual natural conditions. Edge cases 25% weight. But let's consider whether there might be other natural mechanisms at play, perhaps less common, but still within the realm of natural astrophysics. Interstellar comets formed in different stellar systems under different conditions than our solar system's comets. Different protoplanetary disk compositions, different temperature gradients, different elemental abundances. Perhaps some stellar environments produce comets with genuinely unusual mineral compositions, nickel-rich, iron-poor relative to solar abundances. If the nickel-to-iron ratio in 3I Atlas's grains is intrinsically high, if this object genuinely contains more nickel than typical cosmic material, then vaporizing those grains would naturally produce strong nickel lines and weak iron lines. No exotic chemistry required, just unusual starting composition. This would tell us something fascinating about the diversity of planetary formation environments throughout the galaxy. It would suggest that our solar system's composition isn't universal, that different stars create different chemical signatures in their planetary systems.
There's another edge case, preferential grain destruction. Perhaps both nickel and iron grains exist in 3I Atlas's nucleus, but for some reason, maybe size distribution, maybe surface chemistry, maybe sublimation dynamics, nickel-bearing grains are exposed and vaporized more readily than iron-bearing grains. Differential processing, or consider temperature stratification. Maybe the regions of the nucleus that are currently active and venting material happen to be nickel-rich layers, while iron-rich layers remain buried and cold. As the object continues heating, perhaps we'll see iron emerge later. These are plausible but less well-supported scenarios. They require more assumptions, more special circumstances, but they're natural. They don't invoke technology. Hypothesis 3. Artificial systems, speculative possibilities. 15% weight. This is speculation. Let's be crystal clear about that. What follows is not established science, but rather thought experiment territory. What if scenarios? The kind of reasoning that gets scientists cautious but curious. If, and this is a significant if, 3I Atlas were an artificial object, what might explain the nickel signature? Spacecraft construction materials often include nickel alloys. Stainless steel contains chromium and nickel. High-temperature alloys used in rocket nozzles and heat shields incorporate nickel for its strength and corrosion resistance. If an object were venting material from thermal management systems, or if surface ablation were occurring as it approaches solar heating, you might detect nickel in the outflow. Advanced propulsion systems might use exotic coolants or working fluids. If a spacecraft were managing heat through active cooling, and if that coolant contained nickel-bearing compounds venting, it would produce spectroscopic signatures. Similarly, if thruster exhaust contained nickel from chamber erosion or propellant additives that would appear in the coma as atomic emission, this hypothesis doesn't require the entire object to be spacecraft. It could be a hybrid, a natural cometary body with embedded technology, a probe disguised as a comet wrapped in ice and dust, using the sublimation process as cover for its activities. The coma provides concealment. The chemistry looks mostly natural with just enough strangeness to make careful observers pause. But, and this is critical, this explanation is ad hoc. It's designed to fit the observations without independent confirming evidence. If you're being scientifically honest, you acknowledge that while this is possible, nothing about physics forbids it. It's not probable based on current evidence. The burden of proof for artificial origin is high. You'd need more than anomalous chemistry. You'd need resolved imaging showing obvious artificial structure. You'd need spectroscopic signatures that cannot be explained naturally. Emission lines from engineered materials, modulated signals, something unambiguous. We don't have that. What we have is chemistry that's strange but explainable through carbonyl processes, morphology that's ambiguous and dependent on leaked amateur imagery, and a trajectory that's convenient but not impossible for a natural object. The sunward anti-tail, natural or navigational. Let's address one more chemical oddity, the sunward jet, sometimes called an anti-tail. Multiple spectroscopic observations reported a feature extending from 3I Atlas toward the sun. Normally, comet tails point away from the sun due to radiation pressure. A sunward extension is unusual, not unprecedented, but noteworthy. The natural explanation. This is a jet of material erupting from the sun-facing hemisphere of the nucleus. The side facing the sun receives maximum heating, so volatiles there sublimate most vigorously. If a jet happens to be oriented along the sun-comet line pointing sunward from our perspective, it creates the appearance of material flowing toward the sun. It's not actually flowing sunward. It's flowing away from the nucleus, which sits between us and the sun. Geometry creates the illusion, but the speculation clearly labeled as such asks, what if this is thruster exhaust? What if we're seeing a forward-facing engine firing to decelerate the object, slow it down, potentially capture it into a bound orbit, rather than letting it escape the solar system? If you're doing a retrograde burn firing your engines opposite your direction of travel, the exhaust would point forward. Depending on orientation, that exhaust could appear sunward from Earth's perspective during the approach to perihelion. This interpretation is seductive because it fits the Oberth maneuver hypothesis we'll explore soon, but it's not required by the data. The natural explanation sunward jet from active sublimation is simpler and sufficient. The chemistry of 3I Atlas is genuinely unusual. The nickel-over-iron ratio is strange. The CO-rich water-pore composition is atypical. The sunward feature is noteworthy. But all of these have plausible natural pathways. Science proceeds by eliminating hypotheses. When the simple, natural explanation fits the data, you don't invoke complexity without cause. Carbonyl chemistry explains the nickel. Interstellar formation environment explains the volatile composition. Active sublimation explains the sunward jet. The morphology, the visual appearance, the structure people see in the images, that's where the tension lives. That's where the leaked footage and amateur observations create cognitive dissonance with the professional spectroscopy. And that's what we explore next, the shape of intention, the geometry that whispers design, and the question of whether pattern recognition is revealing truth or merely reflecting our deepest hopes and fears. Let me tell you about the human brain's most useful and most dangerous capability, pattern recognition. Evolution built us to see patterns, to spot the predator in the underbrush, to recognize faces in crowds, to detect agency, intention, purpose, deliberate action, because things with agency can help or harm you, and distinguishing them from mere randomness is a survival skill. This capability made us successful, but it comes with a cost. False positives. We see faces in clouds, animals in rock formations, messages in coincidences. The neural circuits that detect real patterns can't help but occasionally fire on noise. So when we look at the alleged imagery of 3I Atlas and see geometric regularity, evenly spaced nodes, symmetrical structure, we must ask, are we detecting genuine artificial design, or are we seeing pattern where there's only chaos and viewing geometry? Let's examine both possibilities carefully. The case for natural interpretation. First, viewing geometry matters enormously. If 3i Atlas is an elongated object, not spherical, but stretched perhaps with a 3:1 or 4:1 length to width ratio, and if we're observing it nearly along its long axis, it would appear as a narrow spindle, even if it's actually a natural, irregular shape. Remember, One-Eye Oumuamua astronomers estimated it had an aspect ratio of perhaps 10:1, making it extremely elongated. If we'd observed Oumuamua end-on, it might have appeared as a compact dot rather than the tumbling cigar we inferred from its light curve. Perspective changes everything. Second, consider multiple jets seen nearly head-on. Comets often develop several active regions, patches on the surface where volatiles sublimate vigorously, creating jets. If 3i Atlas has jets erupting from multiple locations along its rotation axis, and if we're viewing those jets nearly head-on, each jet would appear as a bright, concentrated spot. The spacing between jets depends on where active regions exist on the surface, controlled by subsurface composition fracture patterns, surface temperature variations. It's not impossible for nature to create regularly spaced active regions. If the nucleus has internal layering, or if fractures form at regular intervals, due to thermal stress, you could get apparent regularity that's actually just geology. Third, image processing artifacts are real and common. When you apply deconvolution algorithms to sharpen astronomical images, you're amplifying high-frequency detail, but you're also amplifying any systematic patterns in your telescope's point spread function. Ringing artifacts appear around bright sources. Apparent structures emerge that don't correspond to real features. Professional astronomers test for this by examining stars in the same field of view. If stars show similar ringing or structure, you know it's instrumental. If only the target object shows it, the feature might be real. We don't have that comparison data for the leaked image because we don't have the raw file, only a compressed video clip. Fourth, forward scattering can create intense brightness in specific geometries. Small dust particles scatter sunlight, preferentially in the forward direction. If viewing geometry happens to align with this scattering sweet spot, natural dust clouds can appear dramatically bright and concentrated, potentially with internal structure, as different grain sizes and densities scatter differently. This effect is phase angle dependent and changes as geometry changes. Testing this hypothesis requires observing 3i Atlas from different viewing geometries and checking whether the bright features change accordingly. That test awaits post-perihelion observations. The case for artificial structure. Now the alternative: what would artificial design look like? And how does it compare to what we're seeing? If you were engineering a probe for interstellar travel, what would you build? Let's think through the requirements. First, shielding. Interstellar space isn't empty. It contains dust, microscopic grains. Yes, but at velocities of tens of kilometers per second, even tiny particles carry destructive kinetic energy. A grain the size of a sand speck hitting at 40 km/s delivers energy equivalent to a small bomb. So you need forward shielding. A Whipple shield, named after astronomer Fred Whipple, is a multi-layer bumper system designed to vaporize incoming particles before they reach critical components. This shield would be mounted at the bow facing your direction of travel. It would likely be reflective, possibly ablative, designed to catch and dissipate particle impacts. And if sunlight hits this shield at the right angle, it glows. It stands out. A bright leading edge, exactly like what Tiago's image and the leaked footage show. Second, structural spine. You need a load-bearing framework running the length of your craft, connecting propulsion at one end to payload and sensors at the other. Along this spine, you mount subsystems, fuel tanks, power generation, communications, maneuvering thrusters, radiators. Each subsystem might have its own thermal signature. Radiators, especially any power system, generates waste heat, and in space, the only way to shed heat is radiation. Radiators glow. They emit infrared primarily, but if they're hot enough, they emit visible light. An active spacecraft with a powered thermal management system could produce evenly spaced bright nodes along its spinal truss exactly corresponding to radiator locations. Third, attitude control, to keep orientation stable or to adjust. Pointing for scientific observations, you'd use small thrusters arranged around the vehicle's center of mass. Fire them in sequence and they create a pattern of bright flashes. If someone captures a long exposure image while you're actively maneuvering, those flashes integrate into discrete bright spots. The spacing, determined by engineering optimization. Symmetry is desirable because it simplifies control algorithms. You'd place thrusters at regular intervals to balance forces efficiently. All of this forward shield, spinal structure radiator arrays, maneuvering thrusters would create exactly the morphology people claim to see, an elongated object with evenly spaced bright nodes wrapped in luminosity looking engineered. The symmetry argument. Here's what troubles careful observers. Symmetry at macroscopic scales is rare in nature. Nature loves asymmetry. Asteroids are lumpy, irregular, shaped by collisions and spin. Comet nuclei are oblate or prolate spheroids, at best more often potato-shaped with jets erupting randomly. The cosmos is messy. When you see regular spacing geometric patterns, bilateral or radial symmetry, your brain flags it as unusual. Sometimes that flag is correct. Crystals, snowflakes, nautilus shells. Nature can create symmetry through self-organizing processes at specific scales, but sometimes the flag is false. You're seeing patterns that aren't there, or you're seeing natural randomness that happens to align into apparent order by chance. The question is, which is 3i Atlas? The leaked image shows regularity that looks designed. 6 or 7 nodes, evenly spaced, uniform brightness. If this is real, if it's not artifact, not processing error, not selective interpretation of noise, then it's either a remarkable natural alignment or it's artificial. There's no middle ground. Either nature produced this geometry through some combination of viewing angle sublimation patterns, scattering effects, and coincidental spacing of active regions, or something made it deliberately. The test rotation and variability. Here's how we distinguish between these possibilities. Watch for rotation. If the bright nodes are physical features attached to a solid object, either natural active regions or artificial structures, they should rotate with that object. The object's spin will carry features in and out of view. Their positions should change predictably over time cycling with the rotation period. If the nodes are optical artifacts, forward scattering, PSF ringing, atmospheric effects, they won't rotate. They'll track with observing conditions appearing and disappearing based on viewing geometry and seeing quality, not following any intrinsic periodicity. If the nodes are on an artificial craft, maintaining fixed orientation using active stabilization, they also won't rotate. But in this case, you'd need to detect the stabilization mechanism, the thrusters that keep the craft pointed in a specific direction despite gravitational torques and solar radiation pressure. High-cadence photometry over multiple nights will answer this question. Take images every few hours, track the nodes, measure their positions, look for periodic motion. That's a falsifiable test. Clear outcome. Science at its best. Has anyone done this? Not publicly, as far as available data shows, and now we're entering solar conjunction, so the test can't happen until November. Again, we wait. Historical precedent. Oumuamua's lessons. Remember the debate over 1i Oumuamua. Elongated, tumbling, accelerating away from the sun without visible outgassing. For 2 years, scientists argued about what it was. Natural comet with unusual composition. Hydrogen iceberg, fragment of a disrupted exoplanet. Light sail pushed by starlight. Dr. Avi Loeb and his postdoc Shmuel Bialy published a paper suggesting the light sail hypothesis. It ignited controversy.
Not because the physics was wrong. Light sails are legitimate technology, and radiation pressure can indeed accelerate objects, but because it crossed a threshold. It entertained the possibility of artificial origin without extraordinary evidence. The scientific community pushed back. Extraordinary claims require extraordinary evidence. Oumuamua's behavior was unusual but not impossible for natural objects. Occam's razor favors simpler explanations. Invoking alien technology when natural mechanisms haven't been exhausted is premature. The consensus settled on weird comet, probably. The acceleration could be explained by sublimating hydrogen ice, which is transparent and wouldn't produce a visible coma, or by selective outgassing from one hemisphere, creating an asymmetric rocket effect. Unusual, yes. Artificial, no sufficient evidence. But notice the questions never fully went away.
Because the natural explanations, while plausible, required special conditions, assumptions about composition structure outgassing rates that are consistent with observations but not definitively proven. Oumuamua taught us that interstellar visitors can be genuinely ambiguous. They can occupy the gray zone between obviously natural and obviously artificial, leaving us uncertain. And now 3I Atlas occupies that same gray zone. Morphology that suggests structure, chemistry that's unusual but naturally explainable, trajectory that's convenient but not impossible. We're forced to sit with uncertainty. The data doesn't definitively prove natural. The data doesn't definitively prove artificial. And rushing to conclusions in either direction betrays the scientific method. So what do? We continue observing. We demand better data. We apply rigorous standards.
And we acknowledge that the universe might be stranger than we imagine, while remaining skeptical of the universe being exactly as strange as we hope. There's one more piece that makes this story compelling. One more element that elevates 3I Atlas from interesting comet to we need to talk. The trajectory, the route this object took through our solar system, the timing of its arrival, the close encounters with planets, the approach angle that brought it near the ecliptic, and most critically, the location where it will reach perihelion, the exact spot where any intelligent mission planner would choose to execute a high-energy maneuver. It's time to talk about the Oberth effect, and why, if this were a spacecraft, its trajectory is perfect. Imagine you're standing on a bridge. You have two stones. You want to throw them as far as possible. With the first stone, you stand still and throw. With the second, you sprint across the bridge as fast as you can, then throw at the moment of maximum running speed. Which stone goes farther? The second one. Dramatically farther. Because the stone inherits your running speed plus your throwing speed. The energies add. And here's the key: the kinetic energy you add through throwing gets multiplied by your existing velocity. The faster you're already moving, the more effective each additional unit of energy becomes. This is the Oberth effect. It's basic orbital mechanics, discovered by Hermann Oberth in the early 20th century, and it's the single most important principle in space mission design for achieving high velocities efficiently.
When you fire a rocket engine, the energy you add to your spacecraft depends not just on the thrust and burn duration, but on your velocity at the moment you fire. The faster you're moving, the more kinetic energy each kilogram of expelled propellant adds to your total energy budget. Mathematically, kinetic energy is 1 tog 2 mv2. Velocity is squared. So increasing velocity at high speeds changes your energy much more than increasing velocity at low speeds. If you're moving slowly and you add 1 km/s, your energy increases a little. If you're moving at 30 km/s and you add 1 km/s, your energy increases tremendously. The deepest, fastest point in any orbit around a massive body is periapsis or perihelion, when that body is the sun. At perihelion, you're moving at maximum velocity relative to the sun because you've fallen down into the gravity well. You're also at the point of maximum gravitational potential energy conversion. This is where you burn. This is where every joule of propellant energy gives you maximum effect. Human missions have used this for decades. Let me give you examples. The Voyager probes. Voyager 1 and 2, launched in 1977, used gravitational assists at Jupiter and Saturn to steal momentum from those planets and fling themselves toward interstellar space. Each close flyby was essentially an Oberth maneuver approach, the planet fall into its gravity, well gain speed, and at closest approach slightly adjust trajectory. The adjustment is small, but it happens at maximum velocity, so the effect on final trajectory is enormous. Voyager 1 is now traveling at 17 km/s relative to the Sun, faster than any chemical rocket could have achieved directly. The Cassini mission to Saturn used multiple planetary flybys Venus-Earth-Jupiter to reshape its trajectory and build up enough velocity to reach the outer solar system. Each flyby was carefully planned to occur at the optimal point for maximum energy transfer. Galileo, the Jupiter probe, used Venus and Earth flybys to gain energy before heading outward. The technique is so established that mission planners routinely design trajectories around multiple gravity assists. Now apply this logic to an interstellar probe. You're an intelligence from another star system. You want to send a reconnaissance craft through this solar system, not to stay forever, but to observe, gather data, and potentially continue to other stars. Or maybe you want to establish a long-term observation platform, monitor this system's development over centuries. How do you design the mission? You aim for the star. You fall sunward from interstellar space-building velocity as you descend into the solar system's gravity well. Your trajectory brings you close to inner planets. Venus, Earth, Mars for observations. Measure their atmospheres. Look for biosignatures. Map resources. Assess technological development if inhabitants exist. Then you reach perihelion, closest approach to the Sun. You're moving at maximum velocity now, perhaps 50-60 km/s relative to the Sun, and you have two options. Option 1, accelerate. Fire your engines along your direction of travel. Add velocity. Because you're already moving fast and you're deep in the gravity, well, the same amount of propellant gives you much more final energy than it would if you burned in deep space. You boost yourself onto a faster escape trajectory. Maybe you're heading to the next star on your survey list. Maybe you're returning home with data. Either way, you're using the Sun's gravity to maximize propulsion efficiency. You leave faster, go farther, with less fuel expenditure than any other maneuver profile. Option 2, decelerate. Fire your engines against your direction of travel. Retrograde burn. Shed velocity. Instead of escaping the solar system, you drop into a bound orbit. Maybe a long ellipse that brings you back to the inner system periodically. Maybe a circular orbit at some intermediate distance where you can loiter indefinitely. You're capturing yourself using the Oberth effect in reverse to maximize the energy you remove from your trajectory. This is how you stay, how you set up shop, how you establish long-term presence without needing impossibly large fuel reserves. Both scenarios are plausible for an advanced civilization. Both leverage the same physics. Both require execution at perihelion. Now look at 3I Atlas's trajectory. Dr. Avi Loeb has been pointing this out publicly since the object's discovery. Let me list the specific features he's noted. First, ecliptic alignment. 3I Atlas approached from a direction within approximately 5 kilometers of the ecliptic plane. That's close. The ecliptic is the plane defined by Earth's orbit, and it's where all the major planets orbit. It's our system's busy highway. If you're visiting from interstellar space and you want to encounter planets, you aim for the ecliptic.
A random interstellar object has no reason to prefer this plane. The galaxy is three-dimensional. Interstellar space is isotropic, no preferred direction. But 3I Atlas came in nearly aligned. Statistically, this is unusual. Not impossible, but low probability. If you sample random directions in 3D space, most won't align with any particular plane. The fact that 3I Atlas does suggests what selection bias? We detect objects that come close, and objects that come close tend to cross the ecliptic because that's where we're looking. Or intentional aiming, second close planetary encounters. The trajectory brought 3i Atlas within tens of millions of miles of Venus, Mars, and Jupiter. Not collisions, not extreme close passes, but encounters that would allow detailed remote sensing if you had instruments on board. Spectroscopy, imaging, magnetic field measurements, atmospheric sampling if you deployed subprobes.
If you were planning a grand tour of this solar system on a single trajectory, you'd design something like this. Efficient, opportunistic, hit multiple targets without massive course corrections. Third mass estimates. This point is contentious, but Loeb notes that 3i Atlas appears more massive than 1i Oumuamua or 2i Borisov based on brightness and activity level. Mass estimates for comets are model-dependent. You infer mass from how much light reflects and how much gas is produced, which depends on assumptions about composition and albedo. So this point has uncertainty. But if 3i Atlas is indeed more massive than expected for its size, that might suggest it's carrying more than just ice and dust. Structure, equipment, propellant tanks, things that add mass without increasing activity. Fourth perihelion timing and location. 3i Atlas reaches perihelion at approximately 1.4 AU inside Earth's orbit, but outside Venus's. This is a sweet spot. Close enough for significant gravitational interaction and solar heating, but not so close that thermal loading becomes destructive. If you're doing an Oberth maneuver, you want to get as deep into the gravity well as you can without risking the spacecraft. 1.4 AU is reasonable for that balance, and the timing solar conjunction, the week when Earth can't watch. Fifth, the sunward jet timing. As we've discussed, spectroscopic observations detected a feature extending toward the sun from 3i Atlas. It's visible, it's active, it's happening right as the object approaches perihelion, exactly when you'd expect a thruster burn if you were doing propulsion. Now, all of these features individually have natural explanations or are within the range of coincidence. Taken together, they create a trajectory profile that's optimal. If you handed this trajectory to a mission planner and said, "Design an interstellar reconnaissance probe flyby," they'd say, "Yes, this works perfectly."
The test post-perihelion trajectory. Here's how we'll know. After perihelion, after 3i Atlas emerges from solar conjunction in early November, observers will measure its position. They'll do this with astrometry precise positional measurements of the object against background stars. Over days and weeks, they'll track where it moves. Simultaneously, orbital dynamicists will calculate where the object should be based purely on gravity. They'll take the pre-perihelion trajectory, integrate forward through perihelion accounting only for the sun's gravity and planets' gravitational perturbations, and predict the post-perihelion position and velocity. Then they compare. Observed position versus predicted position. If they match within measurement uncertainty, 3i Atlas followed a purely gravitational trajectory. No burn, no Oberth maneuver. Natural object confirmed, probably.
If there's a systematic deviation, if the object is consistently ahead of or behind predictions, or offset in a direction perpendicular to the expected trajectory, that means a force we didn't account for acted on it. A delta V, a change in velocity. Comets experience non-gravitational accelerations regularly. Asymmetric outgassing creates rocket effects. But those effects are typically small millimeters per second, per day at most, and they're somewhat random, pointing in directions determined by nucleus rotation and active region locations. If 3i Atlas shows a large systematic deviation, hundreds of meters per second or more, pointing in a specific direction consistent with an Oberth acceleration or deceleration, that's when the hypothesis gains real weight. If the deviation points along the velocity vector acceleration scenario, it suggests the object boosted to a faster escape. If it points opposite the velocity vector deceleration scenario, it suggests the object shed velocity and may have captured into orbit. Orbital mechanics is precise. There's no ambiguity in the math. The observations will tell us the answer. Within a month after emergence from conjunction, we'll know. Not speculation, not interpretation, just data and physics. This is science at its most beautiful, a prediction, a test, a clear outcome that distinguishes hypotheses. And we're about to conduct that test. Right now, as you listen to this, the object is approaching or passing through perihelion. The moment is happening. If something is burning, it's burning now, and we can't see it. The sun is in the way. The curtain is drawn. All we can do is wait for November, wait for the object to emerge, wait for the telescopes to acquire it, wait for the astrometry to accumulate, wait for the calculations to complete. And then we'll know if 3I Atlas is following Newton's laws alone,
or if something added velocity where none should exist. But the trajectory isn't just about propulsion efficiency. It's also about reconnaissance, about visiting multiple worlds on a single pass. And when you examine where 3I Atlas came from and where it's been, the trajectory tells a story of a visitor surveying the neighborhood systematically. Let's trace that route.
Space is big. Douglas Adams famously wrote, "Space is big." You just won't believe how vastly, hugely, mind-bogglingly big it is. He was right. And because space is so big and so empty, the odds of anything randomly arriving at our solar system from interstellar space are vanishingly small. The nearest star system, Alpha Centauri triple star system, 4.3 light-years away, is 25 trillion miles from us. That's 40 trillion kilometers. If you scaled the sun down to the size of a basketball, Alpha Centauri would be another basketball 600-800 miles away. The space between is empty, profoundly existentially empty. For an object to arrive here from there, it must be aimed, either by gravity perturbed over millions of years by stellar encounters, galactic tides, random walks through the potential well of the Milky Way until it happens to fall sunward, or by intent, deliberate launch, trajectory design, mission planning. Random interstellar objects should arrive from random directions. The galaxy is three-dimensional. There's no preferred orientation. The plane of the Milky Way is flat on galactic scales, but on the scale of individual star systems separated by light years, there's no reason an incoming object should align with anything in particular. And yet 3I Atlas approached from within approximately 5 degrees of the ecliptic plane. Let me emphasize what this means. The ecliptic is our plane. It's defined by Earth's orbit around the Sun. The other planets orbit within a few degrees of this plane because we all formed from the same rotating disk of gas and dust 4.6 billion years ago. The ecliptic is parochial to our solar system. It's meaningful here, but it's meaningless in interstellar space. An object coming from another star system has no business knowing about our ecliptic. Its trajectory should be determined by its initial velocity from the source system, the gravitational influence of stars it passed near during its journey, and the overall galactic potential. None of these factors preferentially align trajectories with distant solar systems' orbital planes. So why did 3I Atlas arrive nearly in our plane? The skeptical explanation selection bias. We're more likely to detect objects that pass near Earth, and objects passing near Earth necessarily cross the ecliptic because we orbit there. Our detection infrastructure survey telescopes, orbital missions is optimized for monitoring the ecliptic plane because that's where asteroids and comets that threaten us orbit. So maybe there are dozens of interstellar visitors passing through the outer solar system at all orientations, and we only notice the few that come close enough and happen to align. This is plausible. Our detection efficiency is biased. But even accounting for bias, the alignment is statistically noteworthy. There's a broad range of possible trajectories that would bring an object close to the Sun, close enough to detect without aligning with the ecliptic. The object could approach from above or below, the plane dive through it at a steep angle,
and we'd still see it brighten as it heated up near perihelion. The fact that 3I's atlas came in nearly parallel to the ecliptic is a coincidence worth noting. And then there are the planetary encounters. The trajectory brought 3I Atlas within approximately 40-50 million miles of Venus in August 2025. Not close by planetary flyby standards, Cassini flew within thousands of miles of Venus, but close enough that instruments aboard an interstellar probe could conduct valuable remote sensing. Venus is fascinating, runaway greenhouse atmosphere, surface temperatures hot enough to melt lead, thick clouds of sulfuric acid. Understanding what went wrong on Venus, why a planet similar in size and composition to Earth became a hellscape, is one of planetary science's key questions. If you're surveying this system, Venus is a high-priority target. Mars, 3I's atlas passed within similar distances in September. Mars is the most Earth-like planet in the solar system, and it might have hosted life billions of years ago when it had liquid water and a thicker atmosphere. Or it might host life now, subsurface in aquifers or hydrothermal systems. If you're checking for biosignatures, Mars is where you look. Jupiter. The trajectory brought 3I Atlas within about 150 million miles during October. That's a distant pass by Jupiter standards, but it's within the Jovian magnetosphere's extended influence. Jupiter's magnetic field is enormous, stretching millions of miles into space.
Flying through or near it would provide data about magnetic environments, radiation belts, and the interaction between the solar wind and a magnetized planet. The Galilean moons, Europa, Ganymede, Callisto, Io, are also potential biosignature targets, especially Europa with its subsurface ocean. If you were planning a reconnaissance mission to this solar system maximizing scientific return on a single trajectory, you'd aim for exactly these targets. Multiple planets, inner and outer system, rocky worlds and gas giants, diverse environments sampled in one efficient pass. Natural explanation coincidence. The object's trajectory happened to bring it near these planets by chance. Gravitational deflections during the approach could have tweaked the path to create these encounters without requiring intent. Mission design explanation. The trajectory was planned to visit these worlds. Initial velocity from the source star system was carefully chosen. Mid-course corrections during the journey ensured arrival at the optimal geometry. This is what you do if you're exploring deliberately. We can't distinguish between these explanations without more data, but the trajectory is convenient, suspiciously convenient, mass and composition puzzle. Dr. Loeb has suggested that 3I Atlas might be more massive than expected based on its brightness and activity level. This claim is controversial because mass estimates for comets are model-dependent and uncertain. Here's the issue: you can't directly measure a comet's mass from a distance. You infer it. You look at how much light it reflects, which depends on size and surface reflectivity, albedo. You look at how much gas it produces, which depends on composition and volatile content. You compare to other comets with known properties and make educated guesses. For 3I Atlas, if you assume typical cometry, albedo, and composition, you get a certain mass estimate. But if the object is darker, lower albedo, you'd need more mass to produce the observed brightness. If it's producing less gas per unit mass than typical comets, maybe due to unusual composition or thick insulating crust, then again, higher mass. Why would higher mass matter? If the object contains structure, internal framework, propulsion systems, electronics shielding that adds mass without contributing to brightness or outgassing. A spacecraft wrapped in ice would appear more massive than a pure ice body of similar size. But this is speculative. The mass estimates have large error bars. Different researchers using different assumptions get different answers. It's suggestive, not conclusive. The anti-tail timing. We've discussed the sunward jet. Multiple observations detected it. The timing aligns with perihelion approach exactly when you'd expect maximum solar heating and maximum sublimation on the sun-facing side.
Natural explanation, vigorous outgassing from the dayside hemisphere creating a jet that appears to point sunward due to viewing geometry. Alternative explanation, retrograde thruster burn, firing opposite the direction of travel with exhaust visible from Earth's perspective as a sunward plume. The latter interpretation fits the deceleration scenario 3I Atlas slowing down to capture into orbit rather than escaping the system. But it requires assuming the object has thrusters, which brings us back to the core question, is it artificial? We're reasoning in circles. The trajectory suggests possible intent. Intent suggests artificial origin. Artificial origin explains the trajectory. This is why we need independent evidence, morphology, spectroscopy, trajectory deviations that can't be explained naturally. The statistical argument. Let's be honest about probabilities. Interstellar objects are rare. We've confirmed only 3 in human history.
Sample size of 3 is too small for robust statistics, but we can reason from detection rates. Astronomers estimate that objects like these pass through the inner solar system perhaps once per year, maybe more. Most go undetected because they're faint, fast-moving, and we're not looking in the right direction at the right time. Better surveys Rubin Observatory starting soon will catch more. If interstellar visitors are common, and if most are natural debris from planetary system formation ejected comets fragments from stellar collisions, then the default assumption is that any individual visitor is natural. But here's the counter-argument. If technological civilizations exist in the galaxy, and if they explore using probes, then some fraction of interstellar visitors might be artificial. Maybe 1 in 1,000. Maybe 1 in 1,000,000. But non-zero. With a sample size of 3, detecting even 1 artificial probe would suggest that technological exploration is common, because finding 1 in your first 3 attempts means the actual frequency is probably higher than you'd guess. This is Bayesian reasoning. Prior probability times likelihood ratio gives posterior probability. If you start with a low prior for artificial probes, say 1 in 10 million, but then observe features that are more consistent with artificial than natural high likelihood ratio, your posterior probability shifts upward significantly. We're not at proof of artificial origin, but we're in the zone where the hypothesis is worth serious investigation rather than dismissal. What happens next? Early November 2025. 3I Atlas emerges from solar conjunction. Telescopes around the world will acquire it. Astrometry begins, position measurements accumulate, orbital analysts calculate the deviation, if any, from gravity-only predictions. Scenario 1, no significant deviation. The object is where Newtonian mechanics predicts. Natural comet confirmed.
The anomalies we've discussed, morphology, ecliptic, alignment, chemistry, are unusual but not impossible for natural objects. We add 3I Atlas to the catalog as an interesting but ultimately mundane interstellar visitor. Science continues. Scenario 2, systematic acceleration. The object is ahead of predictions, moving faster than expected in a direction consistent with prograde burn at perihelion. It boosted its escape velocity. It's leaving the solar system faster than it arrived. This requires explanation. Outgassing could account for small deviations, but if the delta V is large, hundreds of meters per second, natural mechanisms struggle. The Oberth hypothesis strengthens. Calls for further study intensify. Scenario 3, systematic deceleration. The object is slower than predicted, having shed velocity in a direction consistent with retrograde burn. It's not escaping cleanly. It's dropping into a bound orbit, or at least a slower, hyperbolic trajectory.
This is harder to explain naturally. Outgassing doesn't slow you down efficiently. The deceleration scenario 3I Atlas staying in the solar system becomes compelling and unsettling. We'll know within weeks. The test is clear. The outcome will speak. But before we reach November, before we get those answers, we need to address the question of secrecy. Because if the leaked image is real, if higher resolution data exists showing clear evidence of artificial structure, why hasn't it been released officially? What reasons, benign or otherwise, might explain withholding information? And how do we distinguish between delayed scientific publication and actual cover-up? That's next.
Let's talk about why scientific data might not be immediately available to the public even when something interesting is happening. Let's start with the mundane reasons, the institutional realities that govern how observational astronomy actually works. Reason 1: data quality and calibration. Not every observation is good. Astronomers deal with this constantly. Clouds, turbulent atmosphere, equipment malfunctions, cosmic ray hits on detectors, light pollution, moon glare, tracking errors that cause the target to drift out of the field of view mid-exposure. When you point a telescope at something, you're hoping for good data, but sometimes you get garbage, and professional scientists don't publish garbage. They wait for the next clear night, the next observing window, and try again. Raw telescope data requires calibration before it's scientifically useful. You have to subtract dark current, the signal your detector produces, even in complete darkness due to thermal noise. You apply flat field corrections to account for variations in pixel sensitivity across the chip. You remove cosmic ray hits, high-energy particles from space that strike the detector and create false signals. You correct for atmospheric extinction. The amount of light absorbed by Earth's atmosphere varies with altitude and wavelength. This process takes time, days, sometimes weeks, depending on the complexity of the instrument and the experience of the team. If someone captured 3I Atlas during perihelion but they're still working through calibration, the data won't be public yet. This is quality control, not conspiracy. Reason 2: proprietary periods. Many observatories grant proprietary time to observers who successfully propose research programs. During this period, often 6 months to a year, the data belongs exclusively to the team that requested it. This gives them time to analyze results, write papers, and submit to journals before anyone else can scoop them. It's a standard practice designed to reward the effort of writing successful proposals and to incentivize careful, thorough analysis rather than rushing to publish half-baked results. If someone has proprietary data on 3I Atlas from a major observatory, they're not obligated to release it immediately. Eventually, it becomes public archived for anyone to access, but not right away. Reason 3: spacecraft safety. Space telescopes like JWST and Hubble have strict operational constraints. Pointing too close to the sun risks damaging sensitive detectors. Solar heating can warp structures, degrade optics, cook electronics. Mission operations teams prioritize spacecraft health over any individual science target. If observing 3I Atlas at perihelion required pointing dangerously close to the sun, the observation might not have been approved. Safety trumps science. The data you want might simply not exist because the risk was too high. Reason 4: bureaucratic coordination. Space science is international. Multiple agencies, observatories, research groups tracking the same object. If one group obtains extraordinary data, there might be discussions about coordinated release. Who announces first? Whose press release goes out? What's the messaging strategy? These negotiations take time. They're slow. Frustratingly slow if you're eagerly awaiting results. But they're not malicious. Just institutional inertia. These are the boring reasons. The mundane explanations that account for most delays in scientific data release. Now let's consider the less benign possibilities. National security implications. If 3I Atlas were determined to be artificial, that information would have strategic implications. Confirmation of extraterrestrial technology means interstellar travel is possible. Someone achieved it, that someone might have capabilities far beyond ours. They're observing us, or at least our solar system, intent unknown.
Governments might decide that public disclosure should be delayed until there's clearer understanding of what's happening and what the appropriate response should be. This isn't necessarily nefarious, it's risk management in the face of unprecedented circumstances. Think about how militaries handle unknown aircraft in their airspace. First, you identify. You scramble jets, get close, try to communicate. You don't immediately broadcast to the public unidentified craft overhead, because you don't want to cause panic before you understand the situation. The same logic might apply here. Extraordinary discovery, unclear implications, caution warranted, fear of panic. History provides examples of astronomical news causing public fear. When Halley's Comet passed through Earth's orbit in 1910, tabloids claimed its tail contained poisonous cyanogen gas that would kill everyone. People panicked. Some sealed their homes, some bought gas masks. None of it was justified. The tail was so diffuse it had no effect, but the panic was real. If 3I Atlas were announced as potentially artificial, without clear, conclusive evidence, similar hysteria could erupt. Institutions might decide that avoiding panic justifies temporary withholding of ambiguous data. Wait for confirmation. Get certainty before disclosure. Don't create chaos with speculation. Again, not necessarily cover-up, just cautious communication strategy. Confirmation before disclosure. Imagine you're an astronomer who captured an image of 3I Atlas that looks clearly artificial. Nodes, structure, symmetry. You're excited. You're also terrified of being wrong. If you release it and it turns out to be an artifact processing error, instrumental glitch, misinterpretation, your career is damaged. You become the person who cried alien. Professional reputation matters in science. So you sit on the data. You show it to trusted colleagues. You request follow-up observations from other telescopes. You wait for independent confirmation. And while you're waiting, the data isn't public. This is self-preservation, entirely human, not malicious, just cautious. The Japanese source. Question. If the leaked footage really originated from Japan, what would that source look like? JAXA, Japan Aerospace Exploration Agency, operates space missions, but none currently positioned to observe 3I Atlas at high resolution during perihelion. Ground-based observatories in Japan have capable telescopes. University research groups maintain instruments. Any of these could theoretically have captured something, but if they did, and if it were significant, you'd expect an official announcement. Press release. Paper submitted to a journal. Data presented at a conference. The absence of official confirmation suggests either the clip didn't come from an institutional source or the institution doesn't want to be identified. What about intelligence assets? Military or intelligence satellites sometimes have capabilities exceeding publicly known civilian instruments. If such an asset captured 3I Atlas, that data would be classified. It wouldn't be released through scientific channels. And if it leaked, it would leak through intelligence communities, not astronomy forums. The watermark UFO 5537, the anonymity, the lack of metadata. This is more consistent with intelligence leak than scientific leak, but that's speculation. What would a real leak look like? Professional astronomical data comes in FITS format. Every FITS file contains extensive metadata in its header telescope instrument, filter exposure, time observation, date, time pointing coordinates, detector settings, observer name, program ID. If someone leaked a genuine FITS file, astronomers could verify authenticity within hours. They'd check the star field against catalogs. They'd verify the point spread function matches that telescope's known characteristics. They'd cross-reference weather data from that night. Forensic verification is possible. What we have is a compressed video clip. No FITS header, no metadata. Stripped of all forensic details. This is suspicious. It's consistent with either deliberate hoax, fabricate clip, add watermark for credibility, or sanitized leak strip identifying information to protect source. We can't distinguish between these without more information. The way forward. Evaluate based on outcomes. If post-perihelion data comes out quickly from multiple observatories, if results are published in peer-reviewed journals, if trajectory analysis shows no anomalies, then the withholding hypothesis collapses. Delays were just normal science operating at normal pace.
If months pass with no new data, if freedom of information requests go unanswered, if observatories that should have captured the object claim corrupted data or failed observations, then suspicion is warranted. We're going to privilege official sources: NASA, ESA, peer-reviewed journals. When we speculate, we'll label it clearly. We're not here to push conspiracy theories. We're mapping the territory between known and unknown, showing you where data ends and speculation begins. But before we conclude, we need to examine the natural object explanation fairly and thoroughly, because there are scientists who've looked at everything we've discussed and concluded unusual yes, artificial no. Let's build their case.
Science doesn't prove things true. It falsifies things false. This is Karl Popper's insight, the foundation of modern scientific methodology. You don't prove a hypothesis correct. You subject it to tests designed to break it, and if it survives those tests, you gain confidence. Tentative confidence, always provisional, but confidence nonetheless. So let's apply this to 3I Atlas. What tests could definitively establish natural origin? What would falsify the artificial hypothesis? Test 1: trajectory deviation or lack thereof. This is the clearest, most definitive test. After perihelion, observers will track 3I Atlas's position and compare it to gravity-only predictions. If there's no significant deviation, if the object is precisely where Newtonian mechanics says it should be, then no propulsive force acted on it. No Oberth burn occurred. The object followed a ballistic trajectory determined purely by gravity. This doesn't absolutely prove it's natural. A spacecraft could choose not to burn, or could time its burn differently, but it removes the strongest evidence for artificial origin. Without trajectory deviation, the case for propulsion collapses. Comets do experience non-gravitational forces. Outgassing creates rocket effects, jets of gas propelling the nucleus like tiny thrusters, but these effects are typically small millimeters per second per day and somewhat random in direction because they depend on rotation state and active region distribution. If 3I Atlas shows outgassing consistent deviations, small variable, consistent with cometry activity levels that supports natural origin, if it shows large systematic deviation hundreds of meters per second or more in a direction consistent with deliberate maneuvering, the artificial hypothesis gains weight. If it shows zero deviation within measurement, uncertainty, natural origin is strongly supported. Test 2. Photometric rotation analysis. High cadence imaging over multiple nights can determine whether the alleged bright nodes are physical features rotating with the object or artifacts that remain fixed in the field of view. Physical features attached to a solid body rotate with that body. If the nodes are real, either natural active regions or artificial structures, they should move predictably, cycling in and out of view with the rotation period. Artifacts don't rotate. They track with instrumental or atmospheric conditions. If the nodes appear and disappear based on seeing quality time of night or telescope configuration, rather than any intrinsic periodicity, they're artifacts. If multiple observers using different telescopes all see the same nodes rotating at the same period, they're real. Then the question becomes natural jets or artificial emitters. Natural jets should evolve over time as sublimation changes the nucleus surface. Artificial emitters might remain constant if they're radiators or structural features. This test is feasible. It requires coordination among observers and consistent good weather, but it's doable, and it would distinguish between real and illusory structure. Test 3. Multi-wavelength spectroscopy. Spectroscopy reveals what's chemically present and how it's emitting light. Natural cometary emissions come from specific molecules and atoms excited by sunlight. The emission lines occur at predictable wavelengths determined by quantum mechanics. If someone detects emission lines that don't match any known atomic or molecular transitions, that's a problem for natural explanation. Unknown chemistry suggests exotic processes, possibly technological. If emissions are narrow-band, indicating a laser-like coherent source rather than thermal or fluorescent emission, that's incompatible with natural processes. Coherent light requires stimulated emission. Nature doesn't do that outside of very specific conditions, astronomical masers, for example, which don't apply here. If emissions are modulated, pulsed in a pattern carrying information-like structure, that's unambiguous evidence of technology. None of these signatures have been reported officially. All spectroscopy to date shows natural cometry molecules, CN nickel CO2 CO. Nothing exotic, nothing technological. If this remains true, post-perihelion natural origin is strongly supported. Test 4 resolved. Imaging from multiple instruments. If Hubble, JWST, VLT, and Keck all independently image 3I Atlas post-perihelion and all see the same elongated node-covered structure, and if that structure shows internal detail inconsistent with natural morphology, then artificial origin becomes compelling. Artificial structure would show things nature doesn't produce. Right angles repeating modular elements, obvious joints or connections, surface features like panels or antennas. Engineers love regularity because it simplifies manufacturing and maintenance. Nature doesn't share this preference. But here's the challenge. At the distances involved, resolving fine detail requires either very large telescopes or very close approaches. 3IR Atlas at 1.4 AU is about 130 million miles away. Even Hubble's impressive resolution, 0.05 arcseconds, corresponds to hundreds of kilometers at that distance. You won't see meter-scale details. You might see gross morphology, overall shape, large-scale brightness distribution, but not fine structure. To really resolve this, you'd need a spacecraft flyby, get within thousands of miles, and take high-resolution images. That's the only way to see unambiguous artificial features. No such flyby is planned. Even if one were approved today, launching and reaching 3I Atlas before it leaves, the inner solar system would be nearly impossible. It's moving too fast. It's leaving, so we're limited to remote observation.
And at remote distances, some ambiguity will always remain. The natural explanation. Strong but not definitive. Let's be clear, the natural explanation for 3I Atlas is robust. Morphology, possibly explained by viewing geometry forward. Scattering deconvolution artifacts and multiple jets seen nearly end-on. Unusual but within natural parameter space. Chemistry. Carbonyl chemistry via NiCO4 explains nickel without iron. Kao-rich environment confirmed by JWST. Mechanism is known and plausible. Trajectory. Ecliptic alignment could be selection bias or chance. Planetary encounters could be coincidental gravitational deflections. Perihelion timing could be lucky geometry from our perspective. Sunward jet, active sublimation from the sun-facing hemisphere exactly as expected for a comet approaching perihelion. None of these require invoking artificial origin. Occam's razor, the principle that simpler explanations are preferable, favors natural.
But, and this is important, explainable naturally doesn't mean definitely natural. Ambiguous data allows multiple interpretations. The natural explanation fits, but it requires stacking several unusual features together. Each individually is plausible. Together, they create a pattern that feels convenient. The artificial hypothesis requires fewer stacked coincidences. One assumption, artificial origin, explains multiple anomalies, but it's an extraordinary assumption requiring extraordinary evidence. We're in the zone where both explanations survive. Neither is proven. Neither is falsified. The data isn't sufficient to decide. What would change the skeptic's mind? I've spoken with astronomers about this. Ask them directly what would convince you that 3i Atlas is artificial. Their answers are consistent, resolved imaging, showing unambiguous artificial structure. Right angles, obviously manufactured surfaces, text or symbols, anything that screams design. Spectroscopic detection of emissions inconsistent with any natural process narrowband, coherent light, modulated signals, unknown. Chemistry not explainable by quantum mechanics. Large systematic trajectory deviation consistent with propulsion. Delta V, beyond what outgassing can produce, pointing in directions inconsistent with random rocket effects. Radio emissions. With structured content carriers at precise frequencies, modulation encoding information response to human signals. If any of these conditions were met, the debate would end instantly. The community would converge on artificial origin. The fact that none of these conditions are met yet is why mainstream science remains skeptical. But skepticism is not dismissal. Good scientists remain open to evidence while demanding high standards. The conversation continues because the data, while not definitive, is suggestive enough to warrant continued investigation. And that brings us to the question that matters most if 3i Atlas is artificial. What does that mean for us? Not just scientifically, not just intellectually, but existentially, strategically, culturally. What happens to humanity the day we confirm we're not alone? Early November 2025. The specific date depends on exact perihelion timing, but sometime in the first week of November, 30th, Atlas will emerge from behind the Sun as seen from Earth. Solar conjunction ends. The object becomes observable again, and within days, perhaps hours, telescopes worldwide will acquire it. Here's what happens next. Immediate astrometry position measurements begin. Observers note where 3i Atlas actually is in the sky, its right ascension and declination coordinates measured against background stars. These positions have uncertainties measured in arc seconds, but over multiple nights the trajectory becomes clear. Simultaneously, orbital dynamicists calculate where the object should be. They take the pre-perihelion trajectory, the orbit determined from July through October observations, and numerically integrate it forward through perihelion. They account for the Sun's gravity, gravitational perturbations from planets, radiation pressure, relativistic effects, everything predictable by physics. The calculation produces predicted positions for November 5th, 6th, 7th, and onward. Then comparison. Observed positions versus predicted positions. Plot the differences. Look for patterns. If the residuals, the differences between observed and predicted, are small and random, scattered around zero with no systematic trend. Then 3i Atlas followed a purely gravitational trajectory. Natural object confirmed with high confidence. If the residuals show systematic offset, the object is consistently ahead of predictions, or behind or displaced perpendicular to the expected path. That's a delta V, a velocity change that gravity alone didn't produce. Comets experience non-gravitational accelerations regularly from outgassing rocket effects, but those accelerations are small, typically millimeters per second per day. Accumulated over weeks, they might produce position offsets of thousands of kilometers. That's detectable, but barely. If 3i Atlas shows deviations substantially larger, hundreds of kilometers to millions of kilometers, corresponding to velocity changes of meters per second or more, that exceeds what outgassing comfortably explains. And critically, the direction matters. If the deviation points along the velocity vector accelerating in the direction of travel, it suggests a prograde Oberth burn, boosting to faster escape velocity. If it points opposite the velocity vector decelerating, it suggests retrograde burn, shedding velocity to capture into orbit or slower trajectory. Random outgassing produces random directions. Deliberate maneuvering produces specific directions, optimized for mission objectives. The timeline.
Within 2 weeks of emergence by mid-November, preliminary orbital solutions will exist. Professional astronomers will have rough answers. The data might not be published yet, but they'll know whether deviations exist. By December, refined orbits will be available. Error bars will shrink. Peer-reviewed papers will be in preparation or submitted to journals. By early 2026, we'll have definitive answers about 3I Atlas's trajectory. Did it burn? Did it deviate? Or did it follow Newton's laws? Exactly. Ongoing spectroscopy. JWST, Hubble VLT, and Keck will continue spectroscopic observations post-perihelion. They're looking for changes in chemical composition as the object recedes from the sun and cools. They're searching for any emission lines that don't fit natural categories, narrow-band features suggesting artificial sources, modulated signals, unexpected chemistry. So far, all spectroscopy has shown natural cometry, molecules, and atoms. If that continues post-perihelion, it supports natural origin strongly. If new features appear, especially after perihelion, when natural outgassing should be decreasing, that raises questions.
Morphology monitoring amateur networks, including Thiago Dobsonian Power and others, will continue imaging 3I Atlas through November and December as it moves away from the sun and becomes easier to observe. They'll look for persistence of the bright shield structure changes in morphology development of a tail, which should appear more prominently as viewing geometry improves and the object continues outgassing. If the morphology remains anomalous, structured node-bearing symmetrical across multiple independent observations from different locations, that's significant. If it evolves into normal cometry appearance, fuzzy coma extended tail as viewing improves, that suggests the earlier anomalous images were artifacts of difficult observing conditions. Radio and infrared monitoring radio telescopes could search for emissions from 3I Atlas. Narrow band carriers at specific frequencies would be unambiguous evidence of technology. Broadband emissions could be natural solar radio bursts reflecting off the object or technological communications radar. Infrared observations could detect thermal signatures inconsistent with solar heating alone. If the object is warmer than it should be, based on sunlight absorption and re-radiation, that suggests internal heat sources. Power systems. Active thermal management, that's a smoking gun. SOHO and stereo data, space-based coronagraphs that potentially observed 3I Atlas during solar conjunction will process and release their data. SOHO's LASCO instruments image the sun's corona continuously. If 3I Atlas passed through their field of view, it might appear as a moving point or streak in the images. Processing this data takes time. The instruments aren't optimized for tracking faint comets, and extracting small, fast-moving objects from solar backgrounds requires careful analysis.
But if successful, this data could provide the only direct observations of 3I Atlas during perihelion, the only view during the blackout window, if thruster burns occurred, if brightening events happened, if morphology changed dramatically, SOHO might have caught it. Release timeline for SOHO data is unpredictable. Could be weeks, could be months, but it's worth watching for. What we're looking for: summary trajectory deviation. The ultimate test. Clear outcome, falsifiable prediction, science at its best, morphological persistence. Do the anomalous features remain visible under better observing conditions, or do they disappear as artifacts should, spectroscopic anomalies? Any emission lines that don't match natural chemistry, thermal excess, infrared brightness exceeding solar heating models, radio emissions, narrowband signals, modulated carriers, structured content,
Rotation analysis. Do the bright nodes rotate with the object or remain fixed, independent of spin? Any one of these, if positive, shifts the conversation dramatically. Multiple positive results would be compelling. All negative results strongly support natural origin. NASA's reassurance context matters. Throughout this story, NASA has emphasized no threat to Earth. The trajectory is well understood. 3i Atlas will not impact us. Closest approach to Earth is 1.8 AU 168 million miles farther than the Sun. No danger. This message is critical. Public safety comes first. The last thing anyone wants is panic over a misunderstood interstellar visitor. But that safety message doesn't address the deeper question, natural or artificial. And if artificial, what does it mean? The trouble implied in this documentary's title isn't kinetic. It's not physical danger from 3i Atlas itself. It's paradigm trouble, existential trouble. The trouble of being a young species encountering evidence, ambiguous, frustrating, incomplete evidence that we might not be alone. That's intellectual danger, not physical danger. But for a species that's defined itself by being the only ones asking questions, it's profound trouble nonetheless. The next few weeks. We're in the waiting period now. The blackout window is open or closing, depending on when you hear this. The object is at or near perihelion. If something is happening, if engines are burning, if maneuvers are executing, it's happening now, and we can't see it. The sun is in the way. Nature and geometry conspire to hide the moment we most want to observe. But that's temporary. In days, not weeks. 3i Atlas will emerge. Telescopes will acquire it. Astrometry will begin. And within a month we'll start getting answers. Not speculation. Not leaked images. Not amateur observations awaiting confirmation. Actual data, rigorous analysis, peer-reviewed results. The universe is about to answer a question. Maybe the oldest question. And we're living in the moment when the answer arrives. Stay curious, watch the sky, follow the science. And remember, whatever 3i Atlas turns out to be, it won't be the last visitor. The galaxy is vast, the stars are many, and the space between them, that profound existential emptiness we thought defined the cosmos, is no longer quite so empty. We're listening now, we're watching, and eventually, one way or another, we'll get our answer.
Let me tell you what we know for certain. Atlas is real. Discovered July 1st, 2025 by the Atlas Survey Network. Third, confirmed interstellar visitor in human history. Approaching the sun on a hyperbolic trajectory at 39 kilometers per second. Perihelion around October 29th, 30th, 2025 at approximately 1.4 astronomical units. Professional observations from JWST, Hubble, VLT, and Keck show cometry morphology, fuzzy coma evidence of outgassing spectroscopic signatures of CN and atomic nickel. The chemistry is unusual nickel without corresponding iron, CO-rich, and water-poor composition. But it has natural explanations through carbonyl chemistry and interstellar formation environment. Trajectory brought it near the ecliptic plane, passing within tens of millions of miles of Venus, Mars, and Jupiter. Optimal for reconnaissance if that's what this is. Coincidence if it's natural.
Timing places perihelion during solar conjunction, the 1-week window when Earth-based telescopes are essentially blind, perfect blackout for unobserved maneuvers, or just unfortunate geometry. Alleged leaked footage from Japanese sources dated October 21, 2025, shows morphology completely inconsistent with professional observations, elongated rigid structure, evenly spaced bright nodes, no coma or tail. Provenance unconfirmed, authenticity unknown. Independent amateur astronomer Tiago captured images October 20th showing anomalous front brightening, compact morphology, no extended tail. Verifiable observation but ambiguous interpretation. And critically, no threat to Earth whatsoever. Closest approach to our planet is 1.8 AU 168 million miles. After perihelion it continues outward. No collision course. No danger. That's what we know. Now what remains unexplained? The discrepancy between leaked imagery and professional observations. Either the leaked images are fake, or they captured something under conditions that revealed features the professional observations missed. We can't resolve this without better provenance or independent confirmation. The nickel over iron ratio in spectroscopy. Carbonyl chemistry explains it naturally, but it's still unusual enough that careful observers pause. The sunward jet timing, active exactly when approaching perihelion, consistent with either vigorous natural sublimation or retrograde thruster burn. The near ecliptic approach angle, statistical outlier but not impossible for natural objects given selection bias in our detection methods. The overall trajectory profile. If you handed it to a mission planner and said, "Design an interstellar reconnaissance flyby," they'd say it works perfectly. But coincidences happen. The universe doesn't avoid configurations that look suspicious to humans. We're in the gray zone. The data doesn't definitively prove natural origin. The data doesn't definitively prove artificial origin. Ambiguity persists despite months of observation and analysis. The responsible scientific position is demand high-quality evidence before accepting extraordinary claims. Natural origin is the null hypothesis. Carbonyl chemistry, unusual but natural composition viewing geometry, effects forward scattering these explain most or all of what we observe without invoking technology. But explained naturally doesn't mean definitively natural. It means we haven't exhausted natural mechanisms yet, so we don't need to invoke alternatives. The burden of proof for artificial origin is high. You'd need resolved imaging showing unambiguous artificial structure across multiple instruments, spectroscopic signatures incompatible with natural chemistry, large systematic trajectory deviation inconsistent with outgassing, radio emissions with structured content, something unambiguous. We don't have that. What we have is morphology that's ambiguous and dependent on unverified leaked imagery chemistry that's strange but naturally explainable, and a trajectory that's convenient but not impossible for random interstellar objects. We're working with leaks, anonymous clips, amateur observations, and incomplete spectroscopy during the worst possible observing conditions. It's tantalizing. It's insufficient. The test ahead. Early November 30, Atlas emerges from solar conjunction. Position measurements begin, comparison to gravity-only predictions. Within weeks, we'll know if trajectory deviated. That's the definitive test. Clear outcome. If no deviation, natural origin strongly supported. If systematic deviation consistent with Oberth maneuver, the conversation shifts immediately. We'll also continue spectroscopy, morphology monitoring, infrared and radio searches. Each observation is another test. Each result either supports or challenges the natural explanation.
Science proceeds by elimination. We're eliminating hypotheses systematically, and within a month or two we'll have eliminated enough ambiguity to converge on an answer. The broader meaning. Whether 3I Atlas is comet or craft, it reminds us that our solar system is porous, not isolated. The boundary between interstellar space and our neighborhood is permeable. Things cross it. Messages arrive in the form of wandering objects, carrying information about conditions elsewhere in the galaxy. Each interstellar visitor redefines our cosmic context. Oumuamua taught us these objects exist and can be strange. Borisov showed us they can be normal. 3I Atlas is teaching us that observation is hard, that data quality matters desperately, and that ambiguity persists even when we try our best. The next visitors, 4I, 5I, and beyond, will be caught by better instruments, observed more completely, characterized more rigorously. The Rubin Observatory will transform interstellar object detection from rushed scrambles to routine science. And if one of those future visitors shows clear, unambiguous evidence of artificial origin, if we finally cross the threshold from speculation to confirmation, humanity will face the oldest question with a new answer. Are we alone? We've asked this question for millennia, looked at stars and wondered, built myths and religions around the possibility of other worlds, other minds, feared the dark and hoped for companions in the void. Now we have telescopes, spectrographs, orbital mechanics, machine learning pipelines scanning terabytes of data per night.
We're asking the question with instruments instead of imagination, and the universe is answering, slowly, ambiguously, frustratingly, but answering. 3I Atlas might be just another comet. Weird chemistry, unusual trajectory, difficult observations during unfortunate geometry. Add it to the catalog. Move on. Or it might be the moment when everything changed, when we detected the first unambiguous evidence of technology from beyond our solar system, when we learned we're not alone and never were. We're in that liminal space, between knowing and not knowing, between one paradigm and another. The data is accumulating, the tests are being prepared, the answer is coming, and all we can do is wait for the sun to move aside, wait for the telescopes to acquire their target. Wait for the astrometry to accumulate, wait for the orbital analysts to complete their calculations. Wait for peer review. Wait for publication. Wait for consensus. The universe is patient. It has been here for 13.8 billion years. It will wait a few more weeks while we figure this out, but we're not patient. We're curious, impatient, desperate for answers, and that desperation is what makes us human. That need to know, that refusal to accept mystery when tools exist to resolve it. So we watch the sky. We build better telescopes. We develop more sensitive detectors. We train algorithms to spot patterns we'd miss. We coordinate internationally. We publish openly. We argue fiercely about interpretation while respecting the data. This is science. Messy, contentious, slow, but self-correcting. Eventually, evidence accumulates. Ambiguity resolves. Truth emerges, tentative, provisional, always subject to revision, but truth nonetheless. The final question. When 3I Atlas emerges from behind the sun in a few weeks, and we finally see where it is and where it's going, will the trajectory tell us we're alone in pondering the cosmos? Or will it whisper that someone somewhere is watching us watch them? Will we find that the universe is silent and indifferent, filled with rocks and ice and nothing more? Or will we discover that the void between stars carries not just radiation and dust, but also curiosity? Questions asked by other minds sent across distances we're only beginning to comprehend. I don't know the answer. Nobody does yet. We're living in the moment before revelation, the pause between question and response. But I know the question has been asked properly now, with instruments sensitive enough to detect the answer if it exists, with analysis rigorous enough to distinguish signal from noise, with a species finally mature enough maybe to accept whatever we find. Keep watching the sky, because whatever 3I Atlas turns out to be, it won't be the last visitor. The galaxy is vast, the stars are many. The silence we thought defined the cosmos is breaking one interstellar object at a time. And somewhere out there in the dark, between suns, the next messenger is already on its way. We just don't know it yet. Stay curious. The universe is listening.